Add the circle to the other, and when we use the word segment, we're just breaking something down into smaller pieces or smaller segments. The segments don't have to be necessarily equal to each other. So we have in the theorem 10.18, if two chords intersect in the interior of the circle, each chord is divided into two segments. So we see chord D, C here. It's intersected with chord AB, and it creates two segments of each chord. And we can find the length of these segments using the theorem or the formula down below, where the segments of one chord multiplied together is equal to the segments of the other chord multiplied together. So here we have, it's written as EA times EB is equal to EC times ED. So we want to do our kind of our color coordinating, where EA is red. So we could say EA times EB, so they're being multiplied together or taking the product. Is equal to the product of ED times EC and the product. So our segments aren't going to be equal. That was a different theorem that we started with early in the chapter. Well, what happens if we perpendicularly bisect this? Now our segments aren't necessarily equal, but when we multiply their lengths of each segment together, they do equal each other. So in our first example, we want to find the lengths of these two chords, ML, chord ML, and chord JK. So this is a chord, and this is a chord too. We'll have to use that above theorem because it's split off into segments. So you don't have to find X. We have to first find X and then plug it back in to find our length. So if we use our theorem up top, that 10.18, we're going to multiply the segments of the chords together. So the first segment, let's split up ML. Chord ML is made up of MN and NL. So we could say MN times NL is equal to then our segments of our other chord, KN times NJ. We are our other one. And now from here we want to plug in what we know. So everything is given as kind of a binomial expression here. So we want to make sure that we're plugging everything in with parentheses so we don't lose anything. So for example, MN is x plus 2. And is going to be multiplied by NL. So I'm putting x plus 2 in parentheses. And I'm also putting NL in parentheses. So NL is x plus 1. On the other side, I'm going to do the same thing, but KN is just one term. It's just x. So I won't plug anything in with that. So I won't put it in parentheses. I'm still going to plug it in. NJ is x plus 4, so that I will want in parentheses. All right. Let's focus on the left-hand side first, since that's the more intensive side. When we have a binomial being multiplied by a binomial, there's two ways we can solve it, and I'll do it off to the side here. Not solve, we can simplify. Two ways you may have learned it. First, box method. Other way, foiling. So I'll do the box method first. I'll show both ways. Or the box method, we split if we're doing a binomial times a binomial, we split up into a 2 by 2 box, where we put our top terms up here, other terms along the side, and we multiply into the box. So we take x times x, that's x squared. 2 times x is 2x. 1 times x is 1x. 2 times 1 is 2. And when we're using our box method, why it's kind of advantageous is because along our diagonal, we'll have our like terms, a 1x and a 2x. So we can combine those so we just have a simplified quadratic. So it'll be written as, we could say x squared plus 3x. We get that from taking 1x plus 2x. And then we have a plus 2. That's one way to do it. Other way you may have learned is if we use our foiling method, x plus 2 and x plus 1. Where we go in foiling, double distribute. Some people call it smiles and rainbows. So you go here to here, there's our rainbows distributing out. And here are our smiles distributing our other one. So the first distribution, you would get out x squared. Your second distribution, you take x times 1, so that's plus 1x. Other way, 2 times x. Last one, 2 times 1. So again, we have the same like terms that we can combine in the middle. So x squared plus 3x plus 2. Whether you do it one way or the other way, this is an important skill you need to be able to do, especially when you get to next year in Algebra 3. You'll do this a lot more consistently. So there'll be an opportunity on the next example. I'm going to let you just make sure you can do it on your own. But going back to this problem, we did both of these to find out that, well, this side is x squared plus 3x plus 2. That's what we plug in. X squared plus 3x plus 2. And on our right-hand side, since we just have a term in front of our parentheses, we don't have to FOIL, we don't have to do our box method. We just have to distribute our terms. So distribute and distribute. So this would be x squared plus 4x. Now at this point, we're still just trying to figure out something that x, or value for x. If we have an x squared and an x squared on either side of our equal sign, those are essentially going to cancel each other out. Because we could subtract an x squared from both sides. So this goes away, then this goes away if we do that. Which is advantageous because then we're just left with, we don't have any x squareds. We're back in the world of things just being linear, which means we only have an x to the first. Now we can go ahead and solve for x. We could take away 3x from both sides. Minus 3x minus 3x. So then this would be 2 is equal to, this would be a 1x or just x. Again, that's our intermediate answer. We need to plug that back in to find our full answer because we're trying to find the lengths of each chord. So the length of chord MN would be 4. And then x plus 1 is 3. So ML has to be 7. I'm just plugging in what I know now back into my problem to get the lengths of the segments. And then this would have to be 2. And this would be 6. So JK is equal to 8 then. All right. We're going to do the same thing for AB and PQ. I'll give you the setup. So it'll be x plus 1, x plus 4 being multiplied together is equal to x times x plus 6. Why don't everybody take like 30 seconds or so? Just do what's highlighted on your own. Just check that you can make sure and do that because it's going to be crucial. This is like a need to know how to do. Or else these problems will get stuck a lot. You gotta know how to FOIL, double distribute, it never goes away. It's one of those things. So this would be, we'd have x squared plus 5x plus 4. This term, this 5x we get from taking, if you were to FOIL it, or in your box on your diagonal, you have a 4x plus a 1x. That gets us to 5x. X times x is x squared. 1 times 4 is 4. So then that's equal to x squared plus 6x. And what I like to do at this point, instead of just writing minus x squared, if you have the same thing on either side of the parentheses, it just cancels out. So I'll just cross them out like that. And now we're back into same spot we were before, where we have x's on both sides, and we just have to solve. So we would subtract 5x from both sides. So 4 is equal to x. We can plug 4 in to find our lengths. AB, the length of that chord would be 4. This is 4, so that's 10. This is 14. The length of QP, this would be 5. This would be 9. Oh, wait. 4, 5, 4 plus 4, no, that's 8. 4 plus 4 is 8. So that's 13. Those are your 2 answers. On the back side, we have very similar theorems in terms of how we find them. But again, as you expected, like we've talked about, what if things intersect on the inside or they meet on the outside? We kind of have another kind of pair of that. But this time we're talking about tangent segments and secant segments. So this first box is just a bunch of definitions that are self-explanatory based off their name. A tangent segment is a segment of a tangent. A secant segment is a section of a secant. And then an external segment is a segment that's on the outside of the circle, or it's external versus internal. But we have to use those definitions for the segments of secant's theorem. This one it looks okay, well, we're just multiplying 2 things together again and setting it equal to the other 2 segments we're multiplying together. But we have to be careful now in what it reads. It says EA times EB. So again, it's just not the 2 segments individually being multiplied together. It's the external segment. So if you want to label this your external segment, like EXT, times E to B, that's your whole secant. So it's your secant times your external segment. Same thing here. Our external segment is EC. Our secant is ED. So again, we're taking the external times the secant length. So in example A, we're given the length of the external segment and the length of, we can find the length of the whole segment, the whole secant. So we could say that RP, if we want to write this out, we could say RP is equal to, RP times, this would be RQ, the whole thing. If it helps to remind you, you could say, well, RQ I can split up into the 2 segments. It's RP plus PQ. That's the same thing as just saying RQ. Then you're guaranteed to not miss a piece then and not accidentally just multiply by 11. You can multiply by the whole segment. So then this other one would be RS times RS plus ST, because that is what RT is. So again, if we plug in what we know, everything is set up for us. We know RP is 9. It's times RP plus 11, so 9 plus 11, is equal to RS is 10. Then RS plus ST, you can write as 10 plus X. On our left-hand side, we could just add these two together and multiply. So 9 plus 11 is 20. Multiply that by 9, you get 180. And then here you would have to distribute into your parentheses. So you get 100 plus 10x, where we take off 100 from both sides. We're left with 80 is equal to 10x. Divide each side by 10. X is equal to 8. And it's asking us just for the value of x, not the length of any of the segments. So we're good to go. Don't have to go any farther. Second problem is all the same letters, so I'm not going to write this step out. Maybe I'll show the more condensed version, where this is just 3 times, this will be 12, is equal to 4 times x plus 4. Again, taking my external segment times the length of my secant, so 3 times 12, 9 plus 3 is 12. My external segment, 4 times the length of my secant, RT, so that would be x plus 4. So again, this is, so we go through, we just multiply this side, 36. We're going to distribute on the other side, 4x plus. 4 times 4 is not 36, it's 16. I think it's 6 times 6. When we subtract 16 from both sides, we have 20 is equal to 4x. X is equal to 5. And that's always something you can go back in and plug in and see if it checks out. If we were to plug in a 5 up here, 5 plus 4 is 9. 9 times 4 is 36, which is the same thing as 3 times 12. So just like you would with the normal equation, you can take your x, plug it back in to check that you made sure that both sides are equal to each other. Would have been the same thing here. This 10 plus 8 would be 100, would be 18 times 100. 180 is equal to 180. Good to go. So the biggest thing, remember, when you're internal, you're just taking the two segments, multiplied by each other. When it's external, you have to take the length of the external plus times the length of the whole secant, is where the two big differences are and kind of where the most mistakes show up. That you would try to just do 3 times 9 here, which wouldn't be right. Do 3 times 12.